In this example, we're going to talk about a dart that is thrown at some angle such that it hits exactly in the center of the bullseye of a dartboard 2.38 meters away, and that from the time it's thrown to the time, so this is delta x by the way, to the time it gets there is 9 seconds. And we're going to cheat a little bit and say that the dartboard is a point particle, because some of what I'm doing is much more complicated if we actually consider the fact that a dartboard or a dart looks much more like a line and an arrow, or really a dart would look more like this. So, feathers on the back, pointed tip. So we're going to ignore the fact that that's what a dart looks like and just think about it as a point. If you haven't watched the video that I called Salmon Projectile or Projectile Salmon on this YouTube channel, go do that first, because I talk about some of the concepts behind a trick that I'll use to solve this problem, whereas here I'm just really going to use that trick. So if you're confused by this or don't understand, wait, how did you know that that happens, go watch the Salmon Projectile video first. So some things I'm going to use to do this: if we think that the person threw the dart such that the height of the dart is exactly the height of the bullseye on the target, then we're not changing our y position overall, we're only changing our x position. And so immediately what I think is it might be handy to think about kinematics and just write this as a y equation. So you think about delta x equals v naught x times t plus 1/2 acceleration in x times t squared. We are doing that just with y. And the trick I'm going to use, that if you don't understand you should really go watch the Salmon video, is that if these are released, if it's released and hits the exact same height, and the only vertical force is coming from Earth's gravitational field, then I can say that my initial velocity in y is exactly the negative as my final velocity in y. So however fast it's going up here has to be going just that fast down here. And I'm only making a claim about the y velocities, just so we're clear on that point. Okay, well, what can I do with that? Well, I know an equation that gets me final velocity from initial velocity, so let's see where this goes. And I want to point out that in this problem, I'm not doing this as if I know what the final answer is. I'm actually just writing down for you what I thought when I immediately solved this problem. So some of these things we actually won't use, but I'm writing out my whole thought process for you. And then we said that this thing is just the negative of the initial y velocity, so negative vi y equals vi y plus gt. And that means that negative 2 vi y equals gt. Just some algebra there. Okay, well, what can I do with that? I know eventually I need to figure out how this dart was thrown to make this happen, and that really means I'm trying to figure out the angle it was thrown at. So that's how we'll know we finish this problem, is if I can figure out what that theta is. Okay, well, vi y is some initial velocity, the resultant vector of the x and y, times sine of that angle. And if I really end up needing it, the x component of that initial velocity is not cosine theta, just looking at the triangle that forms. Well, I can at least make a substitution here. I can take this vi y, put it in here, so that gives me negative 2 v naught sine theta equals gt. Well, I'm in trouble. I don't know what v naught is. I don't know what theta is. What will I do? Well, I have another equation that involves theta and v naught. So maybe using these two together, I could somehow figure this out. So let's see what's going on there. I noticed that the problem gave me my delta x and my time. If there are no forces causing acceleration in x, then my x velocity is constant. So let me write that down. If a x is 0, then any change in my x velocity, so my x velocity stays constant. And if we're just throwing the dart, there won't be anything after we've thrown it causing any acceleration in x. So that's a fair thing to use. So I'm going to take this equation here and solve it for v naught, because I know I need to get something here, v naught, and I can find my x velocity. In fact, let's go ahead and do that. So my initial x velocity, which is my x velocity the whole time, is delta x over delta t, and if I just substitute in those numbers, delta x and t, I get 5.3 meters per second. And so I can write down that Vix equals v naught cosine theta, and that is equal to 5.3 meters per second. Therefore, v naught is 5.3 meters per second over cosine theta. So I just took this part of the equation and solved it for v naught. And now I have something that I can take and put in for v naught. And hopefully that will give me just one thing I don't know. So negative 2 times 5.3 meters per second over cosine theta times sine theta. So notice I just substituted in for v naught equals gt. Where ultimately it's just in theta, so let's try to isolate that. I'm just going to multiply these two numbers together to get negative 10.6. Sine over cosine is tangent theta equals gt. And so if I divide by negative 10.6 and take the inverse tangent, this becomes theta equals inverse tangent of gt over negative 10.6. And then if I start subbing things in, that's inverse tangent of negative 9.8. They gave us t per second squared times t, 0.449 seconds over negative 10.6 meters per second. That's what that negative 10.6 is. And if I grab a handy dandy calculator, I find out that theta is about 22.5 degrees.